Ma'am,
Yes.
ma'am, in week 10, lecture 2 and lecture 8 are missing.
Oh, lecture 2 and lecture 8 are the same?
Missing from the course portal.
Oh, is it? Oh, I didn't know this. Oh my god. Okay, let me check with the team right away. Yeah, I informed the team already. Okay. Yeah, thanks for letting us know, Satyam. Yeah. Good evening, Muthu Krishna. Um, okay, probably let's
Good evening.
begin the session. All right. Sir Tony is here, Professor Tony. Uh, he he's going to take the live session for today. He is also another instructor like me for this course. Uh, yeah. Tony sir, would you like to take over?
Good evening, sir.
Good evening. Thank you, ma'am. So, how does this proceed, madam? Like, they can ask questions, doubts, or something like that?
Exactly. So if they have any questions related to the week content, they would be asking the questions. If they are unable to solve any assignment problems or anything, if there is some topic that is not clear to them in the week content, probably they will be asking about the topic and they would be briefing it. Yeah.
Okay.
That's how the usual session goes. Yeah. Muthu and Satyam, you can go ahead and ask like whatever your doubts regarding week 10 to Sir Tony. Okay.
Yeah, yes. Ma'am. Uh,
Sorry, so I would be leaving this session. Okay.
okay,
The
ma'am.
session is
I
being
understand.
recorded. Yeah, please. Yeah, sir is here for you guys today. All right. Yeah.
Yeah,
Thank you.
sure. Okay.
Yeah, so just to give some background, sir is a well experienced professor. He worked in a few colleges already and now he joined the NPTL team. Like, we are privileged to have Professor Tony in our team. Yeah, he's uh, so much experience. So, like, have a good conversation with him so that, like, yeah, you guys will learn a lot from him. Yeah, thank you. Yeah,
Okay.
session is being
Mm.
recorded, sir. So, Tony, sir, if you would like to touch upon any topic, like if you think that would be helpful for the students, you can even discuss in this live session because it is being recorded and it will be uploaded in the YouTube later so that other students will be viewing later.
Okay, sure, ma'am.
Yeah, thank you. Thank you, everybody. Bye.
Thank you.
Thank
Yeah,
you, ma'am.
yeah. Bye.
Okay. So, if you have any doubts, the assignment, what is that, practice questions you can ask. Then later, any question you want me to discuss, you can ask. I will discuss that first.
Yeah, hello, sir.
Yes, tell me.
Yes, sir. Sir, it's regarding some query in course portal, actually.
Oh, course
Uh,
portal queries, actually I'm very new to this. So course portal queries, I think madam only will be knowing. I thought subject
yeah, sure,
wise
sir.
only. Subject wise, in that assignment, anything you have any doubts, you can ask. Because portal, I have not yet physically joined there, so I will ask Jashwanti madam to address that.
Yeah, sure, sir. Maybe I send her the email
Okay.
regarding.
Uh,
So, sir, I have doubt on quiz 2 on some question. May I ask that?
okay. Quiz two. Which one was that? This week 10, you don't have any doubts, correct? Quiz two. Okay. Quiz two questions I don't have. Which question was it?
Uh, I think one three questions, sir.
Okay. Okay. Now ask.
Yes, sir. I have the question IDs. Will that be helpful in finding the question?
Can you read out the questions? Because I have asked madam the questions, but I don't have the questions with me. So she will
Okay.
share the document, or you can read out.
Yeah, sure, sir. Or else, shall I share my screen, sir? Will that be good?
Okay.
Yeah, yes. 1 minute, sir.
You're sharing.
Sir,
Ah, which is the question? Okay, now I got the question paper, so you can tell me which question was it?
yes. Uh, Yeah, yes, sir. This question.
Question that's dx of t by this one,
Yes,
no?
sir.
Dx of t by dt.
Yeah, yes, sir. Yeah, yes.
Dx of t by dt square. This one is to check whether the system is
Linear or
linear or not. Okay, I will share my screen.
okay.
Are you able to see this Word file?
Yes, sir.
Okay, so this is the question, I think. Dx of t by dt plus t square x of t equal to 2t plus 5 into y of t. Correct. This is the question, right?
Yeah, yes, sir.
So the question is check whether the system is linear or not. Okay. So in this case, first what you have to do is first we have to we have to write the differential equation when a particular input x1 of t is applied. Okay. So linear system means it will be satisfying superposition theorem. I think you know that, correct? So first we will be giving an input of x1 of t. Okay. First I will give an input x1 of t. Okay, any input x1 of t. Then I will give an input which is x2 of t. So first I will give an input x1 of t and then check what is the output. Then I will give an input x2 of t and then I will check what is the output. Okay. Then what I will do is I will give an input which is a weighted combination of this. So this I am going to write. I hope this is x1 of t will produce. Okay. First I am going to write from this equation I can write y of t. Okay. So what is y of t from this? Y of t is equal to 1 by 2t plus 5, correct? Into this whole thing. Any doubt in this? From this original
No, sir.
equation, because y of t is my output and x of t is the input. So it would be better if you can write y of t in the left side, or you can proceed as usual also, no problem. Okay, so this is how the first method you can do. Is there any doubt in this? Now what we
No,
will
sir.
do is we will find the output of the system when an input x1 of t is applied. Okay, I'm going to find that. What is the output of the system when the input x1 of t is applied? So what will happen? This, wherever this x is there, y will be replaced with y1 of t, which is the output when x1 of t is applied. And this will become what? x1. Any doubt in this?
No, sir.
So when input x1 of t is applied, the output will be 1 by 2t plus 5 whole into dx of dx1 of t by dt plus t square x1 of t. So similarly, I can write what is the output of the system when the input x2 of t is applied. What will that be? It will be just y2 of t is equal to 1 by 2t plus 5 x2 of t plus x2 dx2 of t by dt plus t square x2 of t. Is this part clear?
Yeah, yes, sir.
Okay. So now what we will do is we will give an output. Sorry, we will find the output of the system when a weighted sum of inputs is applied. Okay. Weighted sum of inputs. That input I'm going to denote as x3 of t. Is this part clear? Okay. So weighted sum of inputs means what? x1 of t plus x2 of t. That is what we gave that. Correct. Now weighted sum of inputs means x1 will be multiplied by some constant, say a. You can denote it as a. So that is what is meant by weighted. Okay, so x1 is multiplied by a, and similarly x2 is multiplied by another constant b. Is this part clear? So I'm going to
Yes, sir.
give this particular input and check what is the output. So let us denote the output as y3 of t. So according to this equation, y3 of t will be nothing but 1 by 2t plus 5 dx3 of t by dt plus t square x3 of t. Any doubt in this?
No, sir.
So now I am going to substitute x3. What is x3 actually? x3 is nothing but ax1 of t plus bx2 of t, correct? So instead of x3, I am going to give that. Any doubt in this?
No, sir.
So now if I expand this, this will become what? 1 by 2t plus 1. This will become a into dx1 of t, sorry, dx1 of t by dt, correct? A into dx1 of t by dt plus b into dx2 of t by dt, correct? This I expanded. Then this will become, what will this be? A t square x1 of t plus b t square x2 of t. Is this part clear?
Yes, sir.
Okay. Now looking into here, this you can see that this is what this I can write as in this particular way. Okay, I'm going to split this x1 terms I am bringing to this side. I can write like this, right? 1 by 2t plus 5 a into dx1 of t by dt plus a t square x1 of t plus b dx2 by dt plus b t square x2 of t. Is that part clear?
Yes, sir.
Okay, now again I am just splitting this. Yeah, x1 terms only I am writing. Plus 1 by 2t plus 5. Is it clear? Correct? Any doubt in
Yes, sir.
this? So now tell me, what is this thing actually? Here again I will take a common from here. So this will become a into, correct? This a I am taking outside and this a I am taking outside. Okay. So this will become a into this particular quantity, correct? Similarly, this will become what? B into, okay, from the last two terms I have taken b outside, and from the first two terms I have taken a outside, correct? Any doubt in this?
No, sir.
Now tell me, what is this actually? 1 by 2t plus 5 into dx1 of t by dt plus t square x1 of t. That is nothing but y1, correct?
Yeah, yes, sir. Correct.
So this can be written as what? y3 of t can be written as a into y1 of t, correct? Plus b into, what is this actually?
Y2.
y2. So you can see that when I applied a weighted sum of inputs, I got a weighted sum of outputs as the output, correct? When I applied ax1 of t plus bx2 of t as the input, I got ay1 of t plus by2 of t as the output. This means that it satisfies superposition theorem, which means that the system is linear. So actually you can write the response or output of the system to a weighted weighted sum of inputs is equal to the sum of weighted outputs, correct?
Yes, sir. Yeah.
Hence, the system is linear. If you did not get like this, then it would have been nonlinear. Okay. Suppose you have, I think you might know, if you have y of t is equal to say e power. Suppose I have, I think you know this, e power x of t. Then this is a nonlinear system actually. Understood? So first what will I do? I will find out y1. So tell me what is y1? Suppose this is the question. y1 of
E,
t will be e of e power x1 of t, correct?
X1,
Similarly, what is y2 of t?
e power x2 of t.
Correct. So what is the output of the system to a weighted sum of inputs? That input I am defining as x3 of t. Okay, x3 of t is equal to a into x1 of t plus b into x2 of t. Okay, that is what is meant by weighted sum. I hope this is clear. Sum of the inputs, but those inputs are multiplied by some constants. That is what is meant by weighted sum of inputs. So now if this is the case, then what is y3 of t? Y3 of t is e power x3 of t, because I know that output is just the exponential of the input. Correct? Now I will substitute x3 of t. But what is x3 of t? This one. So instead of x3 of t, I am substituting this. Clear? Any
Yes,
doubt?
sir.
Okay. So this is not actually the weighted sum of outputs, correct? So this can be written as what? E raised to a x1 of t, correct? Into e raised to b x2 of t, correct?
Yes, sir.
But this is not equal. This is what actually y1 of t into y2 of t, correct? Sorry, it cannot be represented as a y1 of t plus b y2 of t, correct? Say for example, I am going to find out weighted sum of outputs. Okay, sorry. So weighted sum of outputs means what? It is nothing but a y1 of t plus b y2 of t, correct? A y1 of plus b y2 of t. So what is that? A into y1, that is this thing, correct? Plus b into y2, which is this. Is this equal to y3?
No, sir.
No. So this is not equal to y3, correct? Which means that the response of the system to a weighted sum of inputs is not equal to weighted sum of outputs. So the system is nonlinear. Is it clear?
Yeah, yes, sir. Clear.
So like that you can check. Always you can check whether the system is linear or not using this method.
Yeah, yes, sir.
Okay.
Yeah, got it.
If you want, I will save and share in this what is it chat window after completing.
Yeah, yes, sir.
Save and keep so that. Any other doubt?
Yeah, yes, sir. Okay.
Okay. Which one is it?
Yes, sir. Shall I share my screen?
Ah, yes.
Yeah, yes, sir. This one. Sir.
Actually, that question number 19 and 20,
Yeah, yes, sir.
actually they have given you full marks or something, I think. 19, that
This
is what madam told. Question number 19 is given full marks to everyone.
this does it include this question also, sir?
Ah, yeah, yeah, yeah. Because that is a continuation of that, I think.
Okay. I mean, so
I
this
will check.
question.
I'll check later. Okay. So I don't know
Oh,
whether,
okay.
but for that it is not required, I think. Because I'll check with madam because she told 19th question is given full marks, something like that.
Yeah, yes,
Any other question?
sir. Yes, sir. So, sir, so out of this, which is
I think
actually the
anyway power it will be delta of t minus n infinity will, because the Fourier coefficients you will be getting one, I think. So if you add according to Parseval's
yeah,
theorem,
yes, sir.
if you add everything, it will become infinite. Because minus infinity to infinity, when you add one, it will be
Yes.
every time you will have one Fourier series coefficient. So if you add it infinite, you will be getting infinite only.
Uh, yeah, yes, sir. So the energy may be infinite, but the power will it also be infinite, sir?
T AK, because power of according to Parseval's theorem, power
Yeah.
is equal to what, summation of the Fourier series coefficients, right?
Uh, yeah. Yeah, yes, sir. I think yes.
So when you add 1 plus 1 plus 1 plus 1 plus up to infinity, minus infinity to infinity, it will
Okay.
become 1.
Yeah. Yes, sir. Okay. Yes, sir. But as you say, two questions are given full marks for everyone. Is it, sir? Or...
I will ask madam because
Yeah, sure, sir.
uh, whether she told some questions they have given full marks.
Okay. Yes. And sir, yes, sir. Likewise, I have one doubt in this answer actually.
Uh-huh.
Um, will we have 2 pi in the denominator? I mean, does it include a 2 pi term in
Fourier
the in?
series coefficient A5 only you have to find, right? So
Yeah,
it
yes,
is
sir.
given that it is periodic with the period 2 pi, correct?
Yeah, yes.
1 minute, let me copy that question. Yeah. Which
Actually,
is that question?
this is the I mean the generic form. I mean this is where A0.
Uh-huh.
So this is actually the continuation of it. Here we have 2 pi on the denominator.
No,
And
a n only you are finding, na? A5 you have to find, right? What is the x of t is given as what?
e power t, sir.
E power t for the time period, it is periodic pi, correct? Pi less than or equal to t less than or equal to pi, correct?
Yeah,
The question is to find a5, right?
yes.
So shall I share?
Yeah, sure.
It is showing, huh? Can you see the word file?
Yes, sir. I think we can.
Here you can see. Are you able to see x of t equal to e power t I have written?
I think it's
Shall I once more I'll share.
yes.
Can you see the screen now?
Yes, sir.
So this is the question, right? It is period. It is told that it is periodic with a period 2 pi, and
Yeah,
it is defined over one period. Sorry, minus pi, right? Is it
yeah,
minus
yes,
pi?
sir. Minus.
Minus pi. So first I will write the general for equation for the Fourier series coefficient. Okay. So ak is equal to 1 by 2 pi, right? 1 divided by 1 by t, right? 1 by t integral. Okay, here integral. Okay, over a period. Okay, so I'll write like this: integral over a period x of t e raised to minus j k omega. Sorry, omega 0 t. Correct.
Yes, sir.
Okay, so so the time period is already given. So t is 2 pi. So from this I can
Um,
find the omega angular frequency also. Omega 0 is 2 pi divided by t, which is 2 pi divided by 2 pi, which is 1, correct?
yes, sir.
So now I am going to substitute here. So this will become 1 by 2 pi. Okay, integral over a period, it is already defined in minus pi to pi, so I'm using that interval as well. Minus pi to pi x of t e raised to minus jk omega 0 t dt. So during omega minus pi to pi, the value of x of t is given as e raised to t. Sorry, correct? E raised to t, e raised to minus jk omega 0 is 1. That also you can substitute. Okay. So now you are asked to find what is the value a5 a3 what was it 5
Yeah,
a5
5, sir.
so I will substitute k is equal to 5. So this will become 1 by 2 pi integral minus pi to pi e power t e raised to minus j 5. Correct? Correctly, right?
Yes, sir. Yes.
And now again I will. So this can be written as e power 1 minus j5. Correct? Integral minus pi to pi e power 1 minus j5 t dt. Correctly?
Yes, sir.
Okay, so this will become a5 is equal to 1 by 2 pi. Sorry, integration is e power j this thing divided by 1 minus j5. Correct? Between the limits minus pi to pi. So this will become 1 divided by 2 pi into 1 minus j5. I'm going to substitute t is equal to pi first, pi minus, so this will become minus pi, right? Done?
Yeah, yes.
Okay. So now this is a5 is equal to, this will become e raised to pi, right? E raised to pi, e raised to minus j5 pi, correct?
Yeah, yes.
This will become e raised to minus pi, e raised to plus j pi. So plus j5 pi. Correct?
Yes, sir.
Okay, 1 by 2 pi, right?
Yeah, the
Okay.
2 pi.
Oh, that one 2 pi is missing in this.
Yeah, yes.
Okay, okay. I will ask Jafshundi madam. I think this only is correct. Because this choice is
Uh,
not there. Huh?
yeah, yes, sir.
Okay. All other things are correct. This term is there. 1 minus j5.
Yeah, yes, sir. 1 minus 5j is there.
Ah, so okay. And this also is there.
Yeah, yes, sir. Even in the exam hall, when I derived, I got this exact expression. Uh, yeah, the 2 pi is actually missing. Even I too think the same. The 2 pi is missing. But this is the actually the closest answer.
So maybe everybody might have answered that only because of that. And anyway, I'll ask also, madam, because I have this question. So
Yeah, yes,
okay,
sir.
this is what we are getting, and this 2 pi will never cancel out with anything. So I think that
Yeah,
2
yes.
pi should be there. Okay. Uh, Anything else?
No, sir.
And this I will take a screenshot and ask madam also. Okay. Okay. Next, any questions? Week 10, any
Wait. Yes, sir. I have a doubt in week 9 graded assignment. Question 5, 6, and 7.
week?
9.
Could you name the question? Let me check. Week 9, huh?
Yes, sir.
Week 9 graded assignment. Huh?
Yes, sir.
Question number?
5, 6, and 7.
Week number 9. In graded only, right?
Yes, sir.
5, 6, and 7, right?
Yes, sir.
Okay, fifth question is this. Na? Consider the signal x of t which has a Fourier transform x of j omega. Another signal y of t is obtained by doing some mathematical operation on x of t, and the Fourier transform of y of t is denoted as y of j omega. It was noticed that the plot of x of j omega and y of j omega is as below. That one only, right?
Yes, sir.
Okay, let me project. Okay. I have copy pasted. You check whether these are the questions. Can you see? Sorry, session. This one, right? First one. Is
Yes, sir.
this? Okay, so the question is this: consider the signal x of t which has a Fourier transform x of j omega. Another signal y of t is obtained by doing some mathematical operation on x of t, and the Fourier transform of y of t is denoted as y of j omega. It was noticed that the plot of x of j omega and y of j omega is as below. Correct. What could be the mathematical operation performed on x of t to obtain y of t? Okay, so this is a straightforward question because frequency response, you can see that the frequency response has expanded, correct? Yes or no?
Yes, sir.
So uh, when will frequency response expand? Only if compression is happening in time domain. Correct. So that sir had already explained that when there is a compression in time domain, okay, then only expansion in frequency will happen. If expansion is there, if compression is there in the frequency domain, then there will be expansion in the time domain. Okay. So what is happening is that here the frequency response has been expanded. Okay. So this means that in time domain, this x of t, y of t is x of at only, such that a is greater than 1. So always remember, in time domain, if you are expanding the signal, the frequency response will get compressed. Okay. And vice versa. In time domain, if you are expanding the signal, the frequency response will be compressed. And in time domain, if you are compressing the signal, then in frequency domain, it will be expanded. Okay. I think in week 9, sir had explained that actually.
Yes, sir.
I will show you here itself using AT. I think using AT, sir had explained it. See here, can you see this part?
Yes, sir.
Are you able to see here?
Sir.
X of CT. Okay, because this property, that is Fourier transform of X of CT, is X of j omega by C whole divided by this property is used.
Okay, sir. Got it.
Do you want me to do that?
No, sir. Okay.
Sir,
Here, suppose you have X of CT. Okay, so the Fourier transform of X of t. Okay. Fourier transform of X of t is X of j omega. Okay, if this is the case and you are scaling the signal, suppose you are scaling the signal X of CT. See here, same thing. Okay, so if you are scaling the signal, then it will become X of j omega by C. Okay, and 1 by mod C. So this is the property, time scaling property of Fourier transform. Is this clear? This is the property that we are using. So suppose C, let us see, let C be 0.5. Okay, if C is 0.5 in time domain, what will happen? C is 0.5 means then X of 0.5 t means what is it actually? Is it expansion or compression? X of 0.5 t.
Expansion.
Are you able to see this? Hello?
Yes, sir.
Hello?
Yes, sir.
You got
yes.
understood this? Sorry, I had muted myself. I did not see. If C is equal to 0.5, then X of 0.5 t is what? Expansion or compression?
Expansion.
Expansion, correct. If that C value is less than 1, then obviously in time domain it will be expanding, correct. Then X of 0.5 t is expansion. So what will happen here? So if I'm substituting X of this as 0.5 t, then this will become what? X 0.5 into by 0.5, correct. But what is X of j omega by 0.5? So this will become 2 into what? X of what? J what?
2 omega.
J2 omega. Now this is what actually? Is it expansion or compression in frequency?
Compression.
So that is what I told. If a signal is expanded in time domain, then it will result in compression in frequency. Is it clear?
Yes, sir.
So here this frequency spectrum is getting expanded, which means that the input, the signal X of t was compressed. That is why the frequency got expanded. Understood?
Yes, sir.
Okay. Now next question was
Uh,
this.
sir,
Ah,
sir, so I'm. It's but little bit not intuitive actually. For I mean, I feel it little bit not intuitive because when we do, I mean, when we compress the signal in time domain,
ah.
uh, how the frequency it holds increases in frequency domain.
No, that is what I have shown here mathematically. Here, what is
Yeah,
happening?
Yeah, the mathematically it's okay,
Uh-huh.
but I mean, why it happens? I mean, why it is in this way? The I mean, how the frequency, how the new frequency gets added when we compress it in the time domain, and how the frequency gets deducted when we expand it on the time domain like that. I mean, why it behaves in this way actually? That's
No,
my
because when the input signal, when the time domain signal is compressed, the Fourier transform, that interval also will change, right? Earlier, if it
yeah,
was from -2 to 2, now it will become from -1 to 1, right?
yeah, yes, sir, yeah. The time period, yeah, yes, it changes.
If you are compressing it, then in suppose the input signal x of t was from -2 to 2, and you are compressing it by 2, then it will be from -1 to 1, right?
Yeah, yes, sir, yeah.
So now if I take the Fourier transform of that signal, it will be from -1 to 1 t.
Yeah, yes, yeah.
Earlier it was from -2 to 2,
Yes, sir.
correct? Earlier
Yeah.
the time period time of integration was from -2 to 2. Now it is from -1 to 1, right? So
Yeah,
if
yes,
e
sir,
power
correct.
minus j to omega t will come, the other one will be from e power minus j omega t to e power j omega t, j omega only.
Okay. Uh, expand.
Suppose you
Okay.
have a signal from -2 to 2. Okay, suppose it is a rectangle signal from -2 to 2 having value 1. Then if you are finding the Fourier transform, it will be integral is from -2 to 2, 1 into e power minus j omega t dt. Correct. So that will
Yeah,
become
yes.
e power minus j omega t by minus j omega between the limits -2 and 2, which means that you will be getting what? E power minus j 2 omega minus e power plus j 2 omega. So here that e power term is 2 omega there. Whereas when you compress, it will become e power omega only.
Yeah,
Then
yes, sir.
that will result in sinusoid of omega, and the earlier one will result in sinusoid of 2 omega, which means
Okay.
frequency is expanded, right?
Uh, okay. Yeah, yes, sir. Yeah, yes, sir. Okay. Yes, sir. Mathematically, yeah, it's makes sense. But when we say it in a normal, I mean, in a layman's term,
Okay, okay.
uh,
I will surely ask this to sir also. Okay,
okay,
till next time.
because when we
You are asking why in expansion? What is the
the
in,
uh,
other than
in
mathematically? What is the
yeah,
what is happening? That is what.
yeah, what is happening behind, because
Okay, okay. I
the
will ask.
new frequencies are introduced. I mean, we are representing time signal in terms of its frequency coefficients.
Okay, I will.
What
I
are
will ask.
the frequencies are
What is
required?
happening? I will ask.
Yeah, yes, sir. Okay. Thank you, sir. Yeah.
Okay, next to this one only, right?
Yes, sir.
This straight away from what is that? The suppose x of t is the input to an LTI system with impulse response h of t. Let the corresponding output be marked as y of t. Let the bandwidth of x of t and h of t be 2 pi and 4 pi. Then which of the following could be the bandwidth of output y of t? So output the output bandwidth will be always less than or equal, okay, less than or equal to the minimum among the two actually. So here the minimum bandwidth of is the bandwidth of the input, which is 2 pi. Correct? So the output bandwidth can be either less than or equal to 2 pi, not more than that. Output bandwidth can never be more than 2 pi. Okay. So sir has proved this. The bandwidth of the output will be always less than or equal to the minimum bandwidth. So here, out of the choices, 3 pi cannot be the correct one because it is more than the minimum bandwidth. 5 pi is also greater than 2 pi. Only pi is less than 2 pi. So that is the correct answer. So the output bandwidth will be always less than or equal to the minimum of the convolution. Okay.
Yes, sir. Sir, could you please explain bandwidth? What is bandwidth?
Bandwidth, I mean, suppose if you have a filter, okay, suppose you have a filter. Take from here some figure. Okay, suppose the frequency response of something is given like this. Yeah, okay, so this is like a low pass filter. Okay, it passes some frequencies and it stops some frequencies. So you can see that at frequency 0, it is having 1. Correct. The value of the frequency response is 1. After some time, it is reducing and going to 0. Okay. So at some particular point, this value of the response will become 1 by root 2 actually. Okay, that is 0.707 it will become. Okay, 1 by root 2 times the original value. So what is happening is that okay, and this will correspond to a particular frequency. Okay, let this frequency be say omega h omega. Okay, so this band from 0 to omega 1 is actually the band of frequencies that this filter will pass. Okay, so that is what is meant by bandwidth of this signal. Okay, this much band of frequencies it is passing. Okay, 0 to omega 1. After that, the gain or the frequency response value is reducing. So that is it. Here also sir might have given this example also, I think. In frequency domain, where are the changes happening? See here. So this is the band for this particular signal. This is the band like that. In frequency domain, where is the system actually visible? So if you have x of j omega like this, and then if you are, suppose x of j omega is like this, and then you are taking x of ct, x of 2t, so which means your signal is expanded. Then what will happen is that this band, this band will get shrink. So the bandwidth decreases. The bandwidth means the band of frequencies. That is what is meant by that. In this here, the band means actually the band of frequencies. So when convolution happens, what is happening is that the bandwidth of the output, okay, if the output is convolution of x of t and y h of t, then bandwidth of the output will be always less than the bandwidth of the minimum of input and impulse response. Okay. So since it is told that it is an LTI system with impulse response h of t, then we can write that output. Okay, output of an LTI system is nothing but the convolution integral of input and the impulse response. So what is happening is that I know that the bandwidth of x of t input is 2 pi and the bandwidth of the impulse response is 4 pi. Then according to that convolution property, what will happen is that the bandwidth of the output will be less than the minimum, less than or equal to the minimum of this. So what will happen is that you can write here bandwidth of y will be equal to, will be, sorry, less than or equal to minimum of the input bandwidth and the impulse response bandwidth. So this will be minimum of 2 pi comma 4 pi. Sorry. Which means that this has to be, sorry, less than or equal to. Which means that this has to be, output bandwidth has to be less than or equal to 2 pi. So here the only choice is pi. Okay, that is why it is asked could be the bandwidth. We are not telling that it will be pi. Okay, we don't know. Okay, so we are just telling that it will be less than or equal to 2 pi. So the only possible answer from here it is 2 pi. Sorry, pi.
Yes, sir.
Now this
Sir,
one. Ah,
so when we say bandwidth,
no.
shouldn't we be mentioning the Fourier transform notation?
Fourier transform only. In frequency domain only we will be telling bandwidth. No?
Yeah, yes, sir.
Ah.
So in this question, the time domain notation is used, right?
Bandwidth of a signal is what is
Okay.
told. See, bandwidth of signal means that is the where that band is happening in x of j omega. Bandwidth of x of t means where is that signal in the frequency domain it is happening. Okay.
Okay.
Bandwidth
So
of input signal means in frequency domain where is that? That is all. We will be telling in time domain only, like bandwidth of in this
yeah.
signal. Like,
Okay, sir. Yeah. Yes. And sir, in this
uh,
high pass filter example that you
low
discussed.
pass.
Okay.
Usually
Yes.
half power frequency we usually use. Okay, so we will tell that if a filter is uh, good if the output of the filter is at least 50% of a, or any amplifier or anything. Suppose you have an amplifier, okay, and it is amplifying sinusoidal signals. Say for example 0 hertz also it will amplify, 1000 hertz also will have amplify. It might not amplify 1 gigahertz with the same gain. Understood?
Yeah. Yes.
Suppose you have an amplifier with a gain of 10. Okay,
Yes.
So at zero frequency, it might amplify 10 gain you will get. At 100 hertz also you will get. At 1000 hertz also you might get. But when you go to 100K and all, you will never get that gain. Understood. So what is happening is that as frequency increases, this gain slowly it will reduce. So what we will tell is, okay, that amplifier is good if at least 50% of the power is transferred. Okay, so 50% power point, half power point means actually it is 1 by root 2 in voltage gain. That is why we usually take 1 by root 2 of the original gain. Half power, 50% power means actually power formula is what? V square by R, right?
Uh, yeah, sir. Correct.
Power is what? P is actually P is equal to V square, voltage divided by resistance, correct? So half power, a half power means it is nothing but 1 by 2 V square by R, correct?
Yes, sir.
Correct. So during this time, at this half power, what is voltage actually? At this time, this can be written as V half, correct? So V half, sorry, V half, V half square by R, correct? Because voltage, power is always voltage square divided by R. So what is V half here actually? V half square is what? It's a
Yeah, V by root 2 square.
V square by 2, correct?
Yeah, yes.
So what is V half? At half power, voltage is how much?
V by root 2.
V by root 2. That is why we usually take that.
Okay. Yeah.
So half power frequency corresponds to a gain of 1 by root 2 times the original.
Okay. Yes. Yeah. Actually, that was the question I was about to ask you.
Half power frequency. Usually we will tell if at least half of the power is transferred, then the amplifier or the this thing filter is good. So
So
that is why we are using that V by root 2. In dB, actually we will take minus 3 dB. Maybe in some circuits you might have studied. I don't know whether you have studied. When we are drawing frequency response and all, we will take 3 dB down from the original value. That is because when you convert this V by root 2 into dB, it will become minus 3 dB. So,
oh, in decimal
because
notation.
decibel. So if you take 20 log of this, what will happen? Okay, so 20 log of 10, okay, of V divided by root 2, correct? This is actually decibel scale. So this will become what? 20 log to the base 10 V, correct? Minus 20 log to the base 10 of square root of 2. If you have calculator, you can check what is this 20 log root 2. Okay.
Yeah.
So you
So
will, if you have calculator, you can check. MATLAB is here. So you can see here 20 into log 10 of square root of 2, correct? See
yes, sir.
here 3.01. That is why usually we'll find a point such that it is 3 dB down, and that is actually half power point. In dB scale, it will be minus 3.
Okay. So sir, this half power, they should be transferred even on this giga frequency scalars.
No. At gigahertz, you can see the at higher frequency, it will be the gain will be very less. So it is that
Mm.
amplifier is useless during that time. We can tell. So I can tell that, okay, suppose you have an amplifier like this. I can tell that, okay, the amplifier amplifies the signals between 0 and omega 1. Okay. After omega 1, it is not a good good
Oh,
amplifier.
okay.
I can tell like that.
Okay.
Understood?
Yes.
That is what they will
Okay.
use.
So after it crosses omega 1, half
It is
of the even half
half
of the
of the
power is
power
not.
is lost. So it
Oh,
is
okay.
not
Yeah.
it is not a useful amplifier, right? After
Oh,
that
okay. Yeah.
frequency, it is not good. I can tell.
Yes, sir. Yeah.
So this 1 by root 2 in dB, suppose this in dB 1 will become what? 0 dB, correct? Because 20 log 1 is 0.
Yeah. Correct. Yes.
And then 0 minus 3. So this point will be minus 3 in dB scale.
Yeah. Yes. Okay.
Okay. Now this one is, we can use the principle of duality actually. So I hope you remember principle of duality. Okay, so principle of duality states that if the Fourier transform of x of t is x of j omega, sorry, okay, then what we want is then Fourier transform of, okay, now this x of t, this x of j omega, capital X of j omega, instead of omega, I am going to put t so that it will become a time domain signal. Okay, is it clear? So this will be equal to, according to principle of duality, this will be equal to 2 pi into x of minus omega. Okay. So this is principle of duality. So if I know the Fourier transform of x of t, then, and I know that it is capital X of j omega, then I can find the Fourier transform of capital X of j omega. Okay. So it is given that Fourier transform of e power is this. Okay. So let us take this as x of t. Okay. So this is the input in time domain. X of t is equal to e power minus j, sorry, e power minus 3t u of t. And it is given that the Fourier transform of that is, this is a standard formula. So you should always remember e power minus alpha t u of t is 1 by alpha plus j omega. So this is j omega, correct? Any doubt till here?
No, sir.
So now I am replacing that omega with t. So what will happen? This will become x of jt is equal to 1 by 3 plus jt, correct? So that is the question that is asked. What is the Fourier transform of 1 by 3 plus jt? Now, according to our principle of duality, Fourier transform of x of jt, is 2 pi x of minus omega. Now, what is x of minus omega? X of minus omega is x of t is this. So x of minus omega will be what? I will replace t with minus omega, correct? Any doubt in this?
No, sir.
Okay. So this one. Okay. So now what will be the Fourier transform of this one, correct? 2 pi x of minus omega, which is 2 pi 3 omega u of minus omega. This one. Understood?
Yes, sir.
So this one always you should remember, okay? This one is a standard result. Like I hope you remember this. E power minus say alpha, okay? Alpha t u of t is alpha plus j omega. Okay, so this is a standard result. Fourier transform of e power minus alpha t u of t is. Okay. Similarly for Laplace transform also, it will become 1 by s plus alpha. Any other doubt? In week 10, you have any doubts? Week 10 assignment you have to do, right?
Yeah, it's I mean,
Ah,
we are just starting the lectures, watching the lectures.
okay, okay. Week 10, right? So, practice.
Sir.
Ah,
Yes, sir. So, sir, could you please inform Jaswanti ma'am regarding this?
2 pi, right?
Yeah, yes, sir. And besides that, lecture 2 and lecture 8 of week
That
10.
already madam has
Oh, okay. Yes.
emailed them. I saw that.
Okay. Yeah, yes, sir.
She has emailed them.
Okay, yeah, yes, sir. Yes, sir. Thank you, sir.
Week 10 practice, right? Okay, maybe this 8 and 9, do you want me to do?
Yeah, yes, sir.
So that this practice. Maybe I will do some other problem so that you can do.
Yeah, sure, sir.
Okay. Okay. So let me write a question. An LTI system is described by the differential equation d square y of t by dt square plus 3d y of t by dt plus 2 y of t equal to 5x of t. Okay. Find the frequency response of the system and hence find the impulse response and response of the system to an input. Okay, x of t equal to e raised to okay using Fourier transform. Okay, suppose this is the question. Okay, an LTI system is described by the differential equation d square y of t by dt square plus 3 dy of t by dt plus 2y of t equal to 5x of t. Find the frequency response of the system and hence find the impulse response and response of the system to an input x of t equal to e power minus 3t u of t using Fourier transform. Okay. So frequency response can be found using okay, using our Fourier transform. Okay. So frequency response of a system is nothing but the ratio, okay, ratio of the Fourier transform of output to the Fourier transform of input. Okay, so it is denoted using h of j omega usually. Okay, so as omega changes, how does the as frequency changes, how the system behaves? That is what is meant by frequency response. Whether the system will pass 0 hertz, whether the system will pass 100 hertz, that is what is, that idea is given by frequency response actually. So frequency response is kind of a gain because it is output by input only. So here h of j omega is how we are going to denote. Okay, so h of j omega is nothing but Fourier transform of ratio of the Fourier transform of Okay, so Fourier transform of output, which is y of t, correct, divided by Fourier transform of input. Okay, so this is the definition. Okay, so here Fourier transform of y of t is what? Y of j omega, correct? And Fourier transform of x of t is nothing but x of j omega. Okay, so Fourier transform frequency response is nothing but y of j omega by x of j omega, where y of j omega is the Fourier transform of the output and x of j omega is the Fourier transform of the input. Is that part clear?
Sir,
Hmm.
can we call frequency response of a system also as the Fourier transform of impulse response?
Ah, yes, obviously we can.
Okay, yes.
Same. Fourier frequency response is also the what is that? Fourier transform of impulse response. Okay,
Yeah,
so
yes.
now I need the relation between y and x in frequency domain. So what will I do? I will take Fourier transform on both sides of the differential equation. Is it clear? So that I am going to convert this into Fourier domain. Is that part clear? So I'm going to take Fourier transform on both sides.
Sir,
Ah,
so is this the first time a system is being defined using a differential equation?
any system you can in most of the physical systems you can define using first order, second order differential equations, like RC circuit sir has shown you. No?
Yeah,
RC
yes.
circuit, RLC circuit. RC circuit will be a first order differential equation. RC circuit can be modeled using a first order differential equation. RLC can be modeled using a second order differential equation. So this here we are giving generally one differential equation, okay, where y is the output and x is the input. That is all. So this is a second order differential equation. Most of the systems can be defined, described using differential equation.
Yes.
RC circuit, I think RC circuit sir has already. So in this problem, I think sir has asked with capacitor as the output, capacitor voltage as the output. Here in this question, it is a resistor voltage across the resistor as the output. So it can be modeled using a differential equation. So once after modeling, what we are doing is this question. Okay, I got
Yes.
the system. Okay, I got that. I know that a particular system is modeled using this particular differential equation. That is what we, like RLC circuit. Obviously, it behaves like a second order system.
Yes.
So now this can be written as I'm individually taking the Fourier transform. So Fourier transform of d square y of t by dt square plus 3 into Fourier transform of dy of t by dt plus 2 into Fourier transform of I of t, correct, equal to 5 into Fourier transform of x of t. Okay. Now here we will be using one property of Fourier transform, okay, which is the time differentiation property of time differentiation property. So time differentiation property states that if if Fourier transform of x of t is x of j omega, then Fourier transform of nth derivative, nth derivative of x of t will be equal to j omega raised to n x of j omega. So this is the time differentiation property of Fourier transform. Okay. So this we will be using here. So please remember this. If the Fourier transform of x of j omega is, sorry, if the Fourier transform of x of t is x of j omega, then the Fourier transform of nth derivative of x of t is j omega raised to n x of j omega. Sir has proved this. You can go through this through that. If you have any doubts, you can ask me that time also. Okay. So please go through that derivation. This one. Okay. So now what will happen is that I'm going to write the equation for this. So what is the Fourier transform of d square y of t by dt square?
Double derivative.
Double derivative. What will be the Fourier transform?
J omega square whole
Correct.
square.
Correct. J omega. Sorry. J omega whole square into y of j omega. Correct. Because here it
Yes.
is y. Correct. Now what is the Fourier transform of t y of t by dt?
J omega.
J omega y of j omega.
Y.
Similarly, Fourier transform of y of t is y of j omega. Fourier transform of x of t is x of j omega. Correct. So now if I see from the left side, I can take y of j omega common. Okay. So here I am taking y of j omega common. So this will become j omega whole square plus j3 omega. Correct. Like this. So this from this I can get y of j omega by x of j omega. Correct. Is that part clear? So what is y of j omega by x of j omega here?
5 by
5 divided by j omega square plus j3 omega plus 2. Correct. This can be written as 5 divided by, I'm just factorizing so that it will become easy, j omega plus 2 plus 1 into j omega plus 2. Correct. This can be factorized like this. Any doubt in this? Is this clear?
Yes, sir.
Okay. So what is this y j omega by s j omega actually?
frequency.
Frequency response. That is h of j omega. Is it clear? So the frequency response is 5 divided by j omega plus 1 into j omega plus 2. Clear? Any doubt?
No, sir.
Okay. To find impulse response, what you have to do? Impulse response is nothing but the inverse Fourier transform of frequency response. Correct. So I just have to find out the inverse. Okay. So this is h of t is equal to Fourier inverse of h of j omega. Correct. Any doubt?
Sir.
You understood this? Fourier inverse of impulse response. Sorry, Fourier inverse of frequency response.
Yes, sir. Sir.
Mm.
So when we write this Fourier transform notation, we generally write j omega in the bracket, right?
I have written here, no? J omega.
Yeah, yes, sir. So is it because, but
You
this
can write
Fourier,
omega also. In some
because
textbooks, omega only
oh,
will be there.
because
But
the only independent, I mean
variable
dependent.
is independent variable only here is omega. So
Okay,
you
yeah,
can
yes.
write in some textbooks it will be h of omega only.
Okay, sir. Yeah, yes.
It doesn't matter.
Yeah, sure. Yes. Sure.
Okay, so Fourier inverse of h of j omega. Right. Okay, so I hope you know this, right? Because this is because we know that output is what? We know that output of a system y of t, output of an LTI system is what? X of t convolution, correct?
HF.
H of t. Okay, so if you take Laplace, sorry, Fourier transform, you will get this as what is that? y of j omega equal to x of j omega into h of j omega. So from that only you are getting h of j omega actually. Okay, so if I take Fourier transform on both sides, this will become y of j omega equal to x of j omega into h of j omega, because convolution in time domain will become multiplication in frequency domain. This is convolution property of Fourier transform. This also sir has proved. Okay, so I just have to find the inverse of frequency response, then you will be getting impulse response. So for that, it is better to use partial fraction expansion. Okay, why? Because already I know the standard result, correct? I know this standard result. So if I express this as a addition of 1 by alpha plus j omegas, then it is very easy to find the inverse Fourier transform. Yes, so that is what I am planning to do here. Okay, so here this is your expression, correct? So I hope you know partial fraction expansion. This will be can be written as what? A divided by j omega plus 1, correct? Plus b divided by j omega plus 2. Okay, you know this, right?
Yes, sir.
So you can find out a. I hope you know this. I usually use this method to find a and b. So whichever method you have studied, you can. Okay, so this is what I follow. Okay, at j omega equal to minus 1. So whichever method you are following, please follow that. So this is 5. Similarly, b will be 5 divided by this into j omega plus 2 at j omega equal to minus 2. 5 divided by j omega is minus 2 plus 1, it is minus 5. Is it clear?
Yes, sir.
So h of t is equal to, if you are using other method, compare coefficients, whatever method you can use. Okay, so this h of t will be equal to Fourier inverse, correct? Fourier inverse of, I can write like this, Fourier inverse of this thing. But what is the value of a? A is 5 and this is minus 5. So you can see 5j omega gets cancelled. This is 10. 10 minus 5, 5. Correct. Okay, partial fraction expansion is correct. So this I can write like this. So this will become 5 into Fourier inverse of 1 divided by, right, minus 5 Fourier inverse of, okay. So now we can use this standard formula. Okay, so that is why I told remember this. Okay, Fourier transform of e power minus alpha t. Okay, so that I am going to use. So can you tell me what is the Fourier? What is the Fourier inverse of 1 by j omega plus 1?
E power minus t.
Correct. E power minus t u of t. Correct. What is the Fourier inverse of 1 by j omega? So it will become e power minus 2.
Minus 2t. ut.
So this is the impulse response of the system. Okay. Understood?
Sir,
Ah,
but since we know e power minus alpha t is equal to, I mean, since we know the Fourier transform of this e power minus alpha t, we are able to find this.
ah.
But what if we end up in some other for combination?
almost everything you have to do partial fraction expansion and find out. Even if it is complex, you can do.
Oh, okay. So we have to
Other than
break them
that,
in.
if it is something else like a rectangular pulse and all, then you know, right? What is it? If it is
Yeah.
mathematically given, almost everything you can represent using partial fractions as first order things. If square is there, then also you can do like 1 by s plus 1 by j omega plus 1 whole square. Then I know that 1 by j omega plus 1 whole square inverse Laplace, inverse Fourier is t power minus alpha t u of t. So some standard that is actually the differentiation in frequency domain property of Fourier transform. So if you know some basic things like Fourier transform of e power minus alpha t u of t is 1 by alpha plus j omega. Then Fourier transform of t into e power minus alpha t u of t is 1 by alpha plus j omega whole square. All these, if you know, then it is very easy to find. Even if it is complex, then also you can find out because you can represent it as a in terms of partial fraction expansion. If it is 1 by j omega whole square plus something, which results in complex root, that also you can find using this.
Yes, sir. So we have to
It is better
do
to
the
remember
partial
this
fraction
partial fraction expansion you have to do,
and
and then
resemble
take it
it
as
into this one. Okay.
uh.
Yeah, yes, sir. Okay.
Same thing will happen in Fourier, Laplace also. There also we will be finding partial fraction. Same will happen in Z transform also. There also we will not be using that formula that is 1 by 2 pi integral minus that formula is there to find the inverse. No? That usually we will not be
Yeah.
using here. It is better to find using partial fraction expansion.
Okay. Yes.
So now last part I'll quickly tell. Okay, so last part of the question is this. Input is given. Okay, so this is the input that is given. So to this system, I am giving this particular input and they are asking what is the output if this particular input is given. Okay, so what is x of j omega? Can you tell me using the standard result? What is x of j?
1 by
1 by e raised to minus alpha t is
j
uh, 1 by alpha plus j omega. Correct.
yeah
So this will become 3
plus
plus
j.
j omega. Okay. So now I know that what is y of j omega? What is y of j omega? Any idea? In terms of h and x. H of j omega and x of j omega. Okay, what is h of j omega? It is the ratio of y of
Y of j.
j omega and x of
X of j.
j omega. So from here, what is y of j omega?
The product of h of j.
Product of, okay, so output of any system in frequency domain is nothing but the multiplication of the impulse response with the Fourier transform of the input. Understood? Is that part clear?
Yes.
So h of j omega already we know it is this, correct? So I'm going to substitute that into 1 by, yeah. So again you can find the partial fraction expansion and you will get the output. That's all. Understood?
Yes.
It is straightforward. So here you will have to do a by plus b by plus c by and find the coefficients a, b and c and then use the standard formula and find the output. Is it clear?
Yes, sir.
If there are some repeated roots, then based on that, I hope you know that also, right? If it is t power raised to e power raised to minus 3 t u of t, then it will become 1 by 3 plus j omega whole square. Understood?
Yeah, yes, sir.
So then you have to take a by 1 j omega plus 1 plus b by j omega plus 2 plus c by j omega plus 3 plus d by j omega plus 3 the whole square.
Whole square. Yeah.
And then you have to find a, b, c, d. Use the standard formula, you will get the answer.
Sir.
Uh-uh.
So earlier you told, did you say as something as a Z transform, sir?
Z transform maybe in I think in signals it is not there. I don't know. Maybe in
Uh,
DSP next.
oh, okay. Yeah. Okay.
DSP you have
So
right next.
will we study it after Laplace or before?
Usually after Laplace, but 12 weeks only is your course. Huh? I don't know.
Yeah, yes, sir. Yeah. Two
Then it
weeks
is
only.
a 12 week only 12 weeks, right?
Yes.
So
This is
I don't know
10 weeks.
whether it is in signals it will be taught or in DSP.
Okay. Yeah.
For this discrete time signal processing, you need a Z transform actually. So they will be teaching that also. Right?
So, sir,
Mm.
the only limitation in Fourier transform is we can't use it on unstable signals, right? So only we are going to Laplace.
Unstable. Oh, what do you mean? Unstable also you can do, right? Suppose you have a system with an impulse response. This one, okay. Suppose impulse response was like this. Okay, then it is obviously one unstable system actually, this one. Then if you
Sir,
find the output,
unstable. Yes.
if you find the output, you will get, suppose you are doing like this, then obviously the impulse response you will never get it as bounded. Suppose you are doing like this, okay. So this will become a divided by j omega plus 1 plus b divided by j omega minus 2, okay. So this will become what, a will be 5 divided by minus 1 minus 2, that is 5 divided by minus 1 minus 2, that is minus 5 by 3 you will be getting, correct. And this will become 2. So 5 by 3 plus 5 by 3. Like this you will be getting. Understood. So now if I take the inverse Laplace transform, you will be get inverse Fourier transform, you will be getting minus 5 by 3 e power minus t u of t plus 5 by 3 e power what? This will become what? What is the inverse of 1 by j omega minus 2? This will become
E
2t u of
power
t.
2t.
Correct. So you can see here impulse response as t tending to infinity, what will be the value? As t tends to
Yeah.
infinity, this will become 0. But this
0.
will never become 0, correct?
Yeah. It will.
Which
Yeah.
means that impulse response is not bounded, which means it is an unstable system. Whereas here you see impulse response. What will be the value of the impulse response as t tends to infinity?
It will. It will be 0.
0. Understood. So obviously it will be bounded if you are taking, if you are absolutely integrating this h of t, you will be getting a finite value, which means the system is Bibo stable, whereas this one is not Bibo stable.
Yeah. So sir, why we move to Laplace from Fourier?
Laplace, I'm not sure. I think it is another tool only. Okay, maybe. Mm, I think because S now that S here only that imaginary part we are taking, right, j omega.
Yes, sir.
Whereas there S is actually sigma plus j omega. So if you look into this first two videos, sir has explained it very nicely. First two videos of Laplace transform in week 11, I think.
Oh,
Huh?
week 11. Okay.
Ah, there he has told why we are going for this Laplace transform.
Oh, okay.
So,
Yes.
so sir has mentioned sigma plus j omega, all those things. So anyway, in week 11 you will be he is telling that here in
Oh, yes, sure.
introduction to Laplace transform. So there,
Yes.
sir. Okay, so based on this, you can try and do those this what is that practice problems first. Okay. So similarly, the same way that I have told, you can try and do. You will get the answer. Then, if the answer is correct, you go for graded. Graded also there is some question based on that.
Yes, sir.
Okay. Any other? This one, what is it? RC circuit, you know, right? RC circuit, sir has already told, I think. Do you want me to show how it is modeled or any RC circuit?
Yeah, yes, sir.
Which one? RC, yeah?
Yes, sir. Yeah.
Okay, I think it is here. Okay, are you able to see this?
Um,
I have not shared.
No, sir.
No, no, I have not shared, I think. Okay. Now you are able to see it.
Yes, sir.
Okay, so this is one RC circuit. Okay, sir has derived for output as voltage across the capacitor. Okay, so here I am taking voltage as the sorry, output as the voltage across the resistor. Okay, maybe in general I will derive it so that you can use it. Okay, so let us denote this as capacitor value as C and the resistor value as R itself. Let this be R. Okay, so resistor and capacitor we have connected in series. So what will happen is that one current will be flowing. Okay, so that current I am marking here. Okay, in this direction maybe. Okay, So this is the current that is flowing. Is this part clear?
Yes, sir.
Okay. So let us describe this using a differential equation and see whether it is correct. Okay. So here what I'm telling is that I'm applying an input x of t, which is a voltage, and the output is the voltage across the resistor, and it is marked as y of t. Is that part clear?
Yes, sir.
Now, what is the voltage across capacitor? What is the formula for voltage across a capacitor? If the current flowing through the capacitor is given, voltage across capacitor in time is equal to what? 1 by C, okay, integral I of t
I
dt, correct? Voltage
yes.
across capacitor is 1 by C integral I. Voltage across inductor is L into di by dt. Okay. Now, what is the voltage across resistor?
I into R.
R into I of t. Here I of t is the current, so R into I of t. So if I apply KVL, what will happen? So if I am starting from here, the first thing that is coming is minus of x of t, correct? Starting from here and going in the direction of current. So it will become minus x of t plus Vc of t, correct? Plus V R of t, correct? Any doubt in this?
No, sir.
Okay. Now here, what is voltage across the resistor is actually the output voltage, correct?
Yes.
So that is actually y of t. Hmm? Correct?
Yes, sir.
So from this expression, what is I of t? 1 by r into y of t, correct? Yes or no?
Yes, sir.
So now I can, now I'm going to substitute here. So what is voltage across the capacitor? It is nothing but 1 by C integral. I want a relation between x and y. So already VR of t is nothing but y of t, correct? Voltage across the resistor is x of t only, correct? Sorry, y of t only, correct? Yes or no?
Yes, sir.
Yes, sir.
Okay. Now I of t I will substitute at this. What is I of t? 1 by r. So I can substitute here, correct? So what will happen? So this will become 1 by RC integral y of t dt plus y of t, correct? So this I can write as this equal to x of t. Hmm? Now if I differentiate this, what will happen? This will become y of t, correct? This will become dy of t by dt. Yes? Is it clear?
Yes, sir.
And this will
Yes.
become dx of t by dt. So you can see that this is a first order differential equation. Understood? So if I am writing it in order, it is actually dy of t by dt plus 1 by rc y of t is equal to dx of t by dt. So this is how I have modeled the system. Understood? Now if you take the Fourier transform, can you tell me what is a Fourier transform? What is the Fourier transform of dy of t by dt?
J omega
Correct. J omega into, so
y
this is
y of j.
correct. J omega into y of j omega, correct. And this is
Y of
y
j
of
omega.
j omega. And what is this? Dx of t by dt.
J omega x of j.
Correct. So tell me quickly what is a impulse I mean, what is it? Frequency response. Can you tell me?
J omega by
Correct. J omega by j
J
omega
omega
plus
plus
1
1 by
by,
X.
that's it. So based on the value of R and C, you will be getting, understood.
Yes.
Suppose R and C are some value, then you have to find out suppose R is given as maybe 2, sorry, 2, and maybe C is given as 1 farad. Okay, then h of j omega will become this divided by 1 by 2, correct? So 0.5. Clear? So now if I take
Yes,
the
sir.
inverse Fourier transform of this, you will get impulse response. But here, since the numerator and denominator coefficients are the same, then obviously you will have to divide it first and then do, correct? Because numerator is also j omega, denominator is also j omega. So this can be written as 1, correct? So this will become, how will I, so this is 1 minus, correct? 1 minus, this can be written as 0.5 divided by j omega plus 0.5, correct?
Yes.
So what is h of t? Can you tell me? What is the inverse Fourier transform of 1?
Del of t.
Del of t. And what is the inverse Fourier transform of this thing?
0.5 into
Hmm.
e power
Hmm.
minus 0.5 t.
Correct. So this is the impulse response of this particular. Is it clear?
Yes.
Okay.
Sir.
Ah,
So so the so we don't need we don't need to produce a impulse to get the impulse response, right? And it is
here, since you are getting del of t as output,
no, sir. I mean,
uh,
without even generating, producing impulse and sending into the system and checking the output, we are able to figure out what is the impulse response
uh,
of the system.
we can, because now you can see, since this is a physical system, you can see that when t is infinity, you can see that it will be approaching zero only, right? You can see that here.
Yeah, yes,
So impulse response is bounded also. It
yeah.
is a stable system also. What I wanted to tell you is that you asked now why from where you got that differential equation. So differential equation
Hmm.
actually is obtained by modeling any physical system. So
Okay.
one physical system is RC. I think in slides, sir has derived with the capacitor voltage as the output. Understood.
Yeah.
So
Okay.
that is why I have shown as here as resistor voltage. Okay, so if capacitor voltage was the output, then obviously y of t is the voltage across the capacitor.
Yes, sir. So even if we take capacitor voltage as the output, it will also be the same. I mean, somewhat different, right?
It will be now, because when you are
Yeah.
connecting, suppose you are giving DC voltage to a capacitor, it acts as open circuit, right?
Yeah.
So
Yes.
finally, if I am giving a step input here, like you are giving a battery DC
Yes.
voltage, that is a step voltage, right?
Yeah. Correct.
Say 2 volt I am giving. Then this capacitor will act as open circuit. So finally the current will be zero, right?
Yeah. Correct, sir. Yeah.
So voltage across the capacitor, voltage across the resistor will be zero. Finally, steady state voltage across the resistor will be 0. Correct?
Yeah.
I mean, if I am applying x of t as 2 volt DC,
Yes.
then what will happen? This capacitor is open now, like this.
Correct, sir. Yeah.
So finally, output across the resistor is 0.
Yes, sir. Yeah.
So final output is 0. But whereas if you had taken voltage across the capacitor as the output, then obviously this y of t is here, correct?
Yes, sir. Yeah.
And what is the output here? What is the final output y of t? It is x of t.
0.
No,
Yeah.
no, x of t. Voltage. Na?
Oh, yeah. Yes. Okay.
So it is what? X of t plus the voltage across the resistor. Is there any voltage across resistor? No, because
No.
circuit is open. So
Correct.
finally output voltage is x of t.
Hmm.
So based on where you are taking the output from, the output will be different. So if I had
Yes, sir. Yeah.
taken output across resistor, the final output will be 0.
Okay.
Whereas if I had taken output across the capacitor, then obviously the output, final output is whatever DC voltage you are applying. Understood?
Okay. Yeah. Yes, sir.
So, but the main thing is that denominator will be the same whatever you do. This j omega plus 1 by RC, it will be always the same.
Yes, sir.
Same here, same thing only here. If you are doing like this, if I had taken voltage across the capacitor as the output, so this is the equation, right? Now voltage across the capacitor is actually y of t. Is it clear? If I had taken like that. Understood?
And if you extend this derivation for a step and ramp function, I mean after doing for the impulse,
Ah,
can you use the same expression to derive for the ramp and unit function? I mean that the DC part you told, no? That one.
yeah, obviously, because impulse response, if you integrate, usually you will get step response. If you integrate step response, you
Okay.
should get ramp response.
Okay, I mean the double integration you have to do after that.
If you do like that.
Okay.
Okay, see, this because step is obtained by integrating the impulse, right? So if you integrate, you will be getting. Similarly, ramp and parabolic input is there. That also you can. There is an input called parabolic input,
Okay.
which is t square by 2 u of t. T square by 2
Yeah.
u of t, t square by 2, which is nothing but the integral of ramp, right? Ramp is what? Ramp is
Ramp is something like
no
I mean it is something
t
slope, no? The slope is
t, right?
increasing.
T.
Yeah, T.
So if you integrate t, what is integration of t?
T square by 2.
That is parabolic.
And there
That
is
is
anything
parabolic
on the
input.
periodic in that sense?
Which one?
I mean something like sinusoidal and I mean that kind of signals.
No, for
So it
that
is having.
sinusoidal, that is why we are using Fourier transform to find at each
Okay,
frequency
okay,
what is
okay. Yeah,
happening.
yeah.
Understood.
Yeah, I understand.
That is where we are using Fourier transform and frequency and all. This is
Okay.
when DC response, usually you can easily find using this is what. Same way here also I am getting frequency response. Na? See here, h of j omega I got like this. Now if I plot the frequency response, you will be getting say this is your frequency response. Correct. Now I know what will happen if I apply 10 hertz. What will happen if I apply 20 hertz? What will happen if I apply 100 hertz? Understood.
Yeah, correct.
Suppose I am applying say 0 hertz. Okay, then obviously it is 0 divided by 0.5, correct? Which is 0. Yes or no?
Yeah, yeah.
if I am applying J, say 10, then which means I am applying a frequency of 10 radians per second, correct? So this is J10 divided by J10 plus 0.5. So this, it will have a magnitude as well as a phase. So based on that, the output will be something. You understood?
Yeah.
So this magnitude, if I take magnitude of this, will be 10 divided by square root of 100 plus 0.25, correct? Whatever value you're getting. Similarly, phase also you will be getting. Understood? So
Yeah.
phase will be this 90 degree minus tan inverse 10 divided by 0.5. Okay, so this, which means that if you are applying, so if I calculate, if I calculate this is what, 10 divided by square root of 100 plus 0.25, correct? You are getting 0.9988. And angle also I am quickly calculating, that is 90 minus 8 and D 10 divided by 0.5. Okay, so this is 2.86 degrees. Understood? So now if I am telling, okay, I applied an input like this, 2 sine 10t. Okay, then I can tell that the output will be 2 into 0. Understood? And sine omega t, sorry, sine 10t plus 2.8624 degrees. Understood? So this is the output that will be produced. I will know that, okay, if I am applying 10 radians per second sine wave, I will be getting this as the output. Is it clear?
Yes. Yes. Yeah. Yeah. This one, yeah, is asking. Thank you.
So for each frequency, you can actually this RC circuit, when you are taking output across resistor, it is a high pass filter. That is why at 0 frequency you saw the frequency response is 0. Correct. Whereas when at 10 hertz, 10 radians per second, it is almost 1. Correct. At infinite, it will what will happen? Suppose I am giving infinite radians per second. Can you tell me what will happen? So this will become limit. If you apply, what will you get? So
So
this
that
is
means, yeah, one by one. Yeah, it means if you
no,
take it.
not one by one, infinity by infinity. No?
Infinity.
Yeah. Yeah. Correct.
So you have, I will apply a limit, correct?
Yeah.
So suppose I am applying, so here limit. Okay, let me put sorry, this is, what is that? Omega, right? Omega, right arrow tending to infinity, correct?
Yeah.
Solely, right? So this is infinity by infinity. So I will apply that L hospitals rule. Then what will happen? This will become
So we can pull out the j
uh,
omega and divide.
that also you can do.
So it will become, I think, one. I think.
Maybe 2, I think, correct? 2 something.
Hmm?
Magnitude, if you take, it will become 2, I think. 2, 0.5, correct. Magnitude, if I am taking, say for example, magnitude, okay. So this is magnitude of this thing I'm taking, okay. So this will become magnitude of, sorry, magnitude of omega is omega, j omega is omega, and this is, okay, like that you can find out. Okay, Okay, like this you can. So as you told, if I'm taking omega out, what will happen? This omega, if you are taking omega out, sorry, from here I'm taking, so omega, correct?
Yeah.
This will become 1. This will become by omega. Okay, so 1 only, correct, correct.
Yeah,
So,
yeah.
so you will be getting 1. Is it clear?
Yeah.
Which means that at low frequency, the gain at 0 frequency, you can see that the gain is 0. Understood? At high frequency, the gain is 1, which means that this circuit that we have drawn here is actually passing high frequencies
High frequency.
and stopping low frequencies. So this is actually a high pass filter. If you had
Yeah. So
interchanged the resistor and capacitor, it will become a low
low
pass
pass.
filter.
Yeah, I mean across the capacitor is low pass. Generally.
Correct, 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 correct. So that here it is shown. Understood. So for any frequency, you can find out what will happen. What will happen if I give this particular frequency? What will be the output in this way? Is it clear?
Sir.
Any other doubt?
Sir.
Ah,
So why we express the system in this differential form? I mean, is it only due to do these all these calculations?
mathematical modeling we are doing. No? So you can almost all systems, physical systems, can be modeled using differential equations. That is why we are studying all these maths, how to solve differential equations, so that
Mhm.
that can be applied to find out what is the output or what is the expected output for this particular thing. So almost all mechanical systems also can be modeled using differential equation. Okay, say for example, mass damper system and all are there. That can be modeled using a second order differential equation, and then you can, if you want to if you want to simulate a particular system, a mathematical model should be there, right?
Yes, sir. Yeah.
So either you will be using differential equation and then going for transfer function analysis, or there is something known as state space modeling. From the differential equations, they will represent it in using matrices. That is what is known as state space model. So that and all maybe you will be studying later. So almost
Yes.
all systems you can represent using mathematical. But for in signals and systems, I think you will be discussing only linear systems.
Yes, sir.
Hello, sir.
Ah, sir.
No, I just asking. You'll be taking further classes in this course. I mean,
Actually, I am assigned for DSP, digital signal processing, which is starting from September, I think.
okay, okay.
I'm just helping now because I'll be joining on 19th only.
Okay, okay. And ma'am, you'll be coming back again, or you'll be only continuing?
Madam will come.
Okay,
Madam is
okay.
the main instructor.
Yeah, I know that. So
Okay.
I was just wanted to request you to, can you do one? I mean, this is a repetition I am asking, but can you take it one more class from the convolution part of starting from there? I mean,
The topic you tell, then I can. Which
no,
one?
I mean, by principle, the definition and then working out some problem, because this time quiz 2, I could able to solve some problem, but I had some problem on from the basic how to derive and then go through that problem. I mean, the solution. So there was some difficulty. I can bring that question next session if you are coming for the next session. and I believe others may be also struggling in that part because we are not very not very comfortable with that. I believe Muthu also can tell something if you want to tell.
You want to
Yes.
know how to find output using convolution integral, or what is it?
Yeah, and then the first thing we want to understand the convolution, and then the whatever the method we adapt on the integration part. Then we approach towards the Fourier series for the periodic signal. So this much we want to again revisit and understand that because I think we are missing on that.
Uh,
Yeah, this is
Yes,
what
so
I am missing. Yeah.
we are thorough in concepts, but when it comes
problems you
to,
want.
yeah,
Yeah,
yes,
yeah. When it comes to problem, how to apply it, then how to put in
and
integration, we are a bit not comfortable actually in that area.
Okay.
we are a little bit struggling in arriving the
No,
expected
one or
solution.
two model questions. If you can show me, I can tell. I don't know what was asked actually.
Yeah, so I
In
can
which
bring
week?
it next because yeah,
In
I
which week
mean
it was asked?
this quiz 2 was from week 4 to 8.
Uh-huh.
Question came, and I think the for week no week 5 to week 8. Yeah.
Okay.
Uh, Maybe we
In that
can do
convolution,
50
in
questions.
okay, I will ask madam to give the questions of quiz 2. In that, whatever convolution is there, you want to know. Is that?
Yes, yes, yeah, and that will be if you are coming next session. I will be great actually for us also.
No, next Saturday session is handled by professor itself, Lakshmi
Oh,
sir.
professor is coming this time.
Oh,
I think so.
Okay.
okay.
Then after that also, if you have doubts, you can post it. You can ask me, no problem.
Okay.
I can do a Google Meet by myself if you want. That time you can ask, no problem.
No problem. So
Mm.
you allow us some time. I will come back on that. Yeah.
It will be better if you ask after 19th. Is it okay after 19th?
No problem. No problem.
Because
Our
I
aim is
am
to
getting
complete
relief from
before.
one institution, so here I'm always busy. So that is why.
No
After
problem. I
19th, I
understand.
will be in campus, so I will be free. So that after 19th, any day, if we can arrange one time, then obviously we
Yeah.
can meet using Google Meet, and you can ask and quiz 2 convolution problems. If you have any problem, I will just go through that and help you out. You
Yeah.
know how convolution, that formula, how it came and all, you know, right? That is,
Correct. We know
you
the
know,
concept, but
x of
to
tau,
apply
h
it,
of t
yeah.
minus tau, h of t minus, that you know,
Yeah.
right? Integral.
Yeah.
Then we can do. I'll bring some problems and then we can do that.
Yeah. Yeah.
Quiz 2 problems we will solve first based on convolution, and then I will ask you some questions. You can work on it. I will also sit with that so that you can tell in between what is the step. So I will type it. If typing is
Yeah.
okay.
Yeah. Yes. Yes. I mean, the way we explained today, I think it is quite makes sense to us, and we can also work out on that. Yeah.
Okay, sure. I will. And then after that, I can make it to a PDF and share to you also, so that you can.
Yeah.
Okay. The only thing is that little time it takes to type because
Yeah.
and
That's
to draw and all it is difficult. That is so.
yeah.
Once I come there, I will take that pad, not pad, that iPad or something, and then for drawing I will use that.
Yeah.
Okay. Any other doubts? Okay. This shall I put it in this chat window? Do you want this?
Yes.
Okay, I will just save it and put in this. All are from here. I mean, where are you guys? Which part of India?
I'm from Bihar, but I am working in Bangalore. So
Okay.
basically,
Oh, I am in Bangalore only. Now I am in Bangalore.
okay.
Okay.
Yes,
How
I
to
am from
share
Tamil
some
Nadu, sir.
Tamil Nadu. To
Yes.
And I'm from UP.
Okay. I don't know how to share. I don't know. Oh, in here, no. Oh, we cannot share any document.
No, I think you have to put in discourse maybe.
Okay, okay, okay.
Yeah,
Then I will follow.
everyone can
PDF
see
link
in
also
discourse.
you can share.
Which one?
PDF link.
Okay, okay,
Yes, sir. We can share a link, but we can't share a document itself.
okay.
Are you in Discord, sir?
Actually, I am very, I am very new to this.
Oh, okay. Yeah.
I, maybe they might have added. I don't know. Here. Okay, then I will ask Jashwanti madam how to share because I am also I am not given that. I think madam only has the privilege to record and all. So maybe
Yes, sir. Sure.
okay. Any other doubts or shall we wind up?
And sir, if you wish, could you please share it about yourself, sir? Because anyhow, we will be meeting soon in next term in DSP.
Oh, you only will be taking DSP. You
Uh,
guys.
yes,
Okay,
sir. We
continuation.
will. Yeah, yes, sir. We will
Uh-huh.
be taking that course next time.
Okay. Well, myself, I'm Tony Abiwarki. I did my BTech and MTech from Kerala only. After that, I was in the teaching field only. I was working with Christ University, Presidency University, and all. I started teaching from 2005. Okay, signals I have taught sometimes, not that much, but okay, I think. Then some other courses I have taught, like integrated circuits, control systems. That is what I have taught till now. Signals, once I have taught. Then what else you want to know? Anything else? I am from Kerala. My native is Kerala.
Yeah, I
Yeah.
understood you in first time itself because I mean the way
Oh,
you are speaking, I can find out that you are from Kerala.
the slang.
Yeah, yeah. So a lot of friends are there in company,
Okay,
so
okay.
they speak in the same
Tone
yeah,
and
so
slang.
tone
Okay.
and slang. Yeah, so it was very easy to guess that. Yeah.
Okay.
In Kerala, which place, sir?
Cochin, Cochin.
Oh, okay. I am near to Kerala actually.
Which one? Which place?
Teni district.
Oh, Teni. Kambam, Teni. That.
Yeah, yes. Near actually, Kambam is 5 minutes away.
Oh, okay, okay.
Yes.
That's good.
Yeah, small town called Uttamapalayam,
Okay.
near to Chinnam.
Uh,
So you are joining IITM. I mean the recent time or uh,
I have joined online on June 1st. Now, physically, I
okay,
will join on 19th. That
okay,
is
okay.
coming Monday. Monday. That is why I told because now I am working in presidency, so I don't have time that much. That is why I was not involved much. But in DSP, I am the sole this thing, so I'm the sole course instructor there.
I think
So,
we are only going to be there mostly.
huh?
I mean, we are only going to be taking up next. I mean, next term DSP.
Okay, okay.
Yeah,
And analog electronics you have studied, no?
not. I mean, we have studied basic in term two.
Okay, okay.
Not in a very deep way. I mean, the way we are teaching this course is taught now of signal and system, not in that way. Yeah, that much.
Okay.
Yes, sir. The course I think will be on the next term, like the analog course.
So that there also I am there.
Oh, okay. Yes.
So you will get bored of me.
No, sir. No. Your teaching was very good, very amazing.
Oh, thank you.
I mean, see, all the teas are really fantastic. I mean, so far, whomever we have met in this course, we have really enjoyed the course, and a lot of help also we have got. So, yeah, it was never boring actually. It was
Okay.
every time learning and going forward.
Okay. Okay. That's
Yeah.
good. Okay, you guys think of a time when you guys are free and you can schedule one meeting.
Yeah.
Okay.
Yeah, yes, sir. Of
For that
course.
convolution, how to do the problems. Okay.
Yeah, I'll search some. Yeah, sure. But some of us are working. Like Prabhanjan sir is working. He's a
Okay.
working professional.
So no, when you guys all are free, you can tell during that
Yeah,
time.
sure. Yeah, sure, sir.
Okay.
Yes, yes. We'll. I mean, we have our WhatsApp communication. We'll discuss this, and we'll
Hmm.
definitely we'll like to have this. I mean, this discussion before our final term.
Sure. Sure. Sure.
Yeah, yeah. So
Next week someday you can plan.
yeah, yeah.
Okay. Shall I exit?
Yeah,
Yeah,
sure.
yeah, yeah.
Yeah,
It's
sure.
Okay.
thank you for your
Okay.
time. Yeah.
Okay.
Yeah,
Thank you.
sir.
Thank you all.
Yes.
Thank
Thank
you,
you.
sir. Thank you for the great session and happy Independence Day in advance.
Yes. Happy Independence Day, everyone.
Yeah, yeah, everyone,
Happy
everyone.
Independence Day.
Yes. Thank you, sir. Thank you, everyone.
Okay.
Good night, sir.
Thank you, sir. Good night.
Good night.